behind here. I am frantically searching for a problem I wanted to show you guys today. I was running late and getting at it. That's not it. Okay. How many? Looks like we have everyone here. Yeah. Everyone doing okay? Ready for the break?
I'm ready.
So I had a funny, I'd call it a funny. My wife and I would call it a funny. So I'm getting ready to run out the door to pick up my son. My boss calls, wants to talk to me about something. It's like wanting to know something specific, some data for analysis I did. And I'm like, trying to pull that up. And then he wanted to set up a meeting with me for next week. It's like, oh, you in the office? Yeah, I'm in the office. I forgot that I had blocked off my calendar for next week thinking that I might take the week off. So it corresponded to the week off with Sac State. So I get a note from him. Hey, you just told me you're in the office next week and it says you're on vacation all next week. What gives? So I'm like, oh no. My boss is this very heavy set South African that doesn't really have a sense. Well, I guess he has a very dry sense of humor, but yeah, he kind of always looks pissed off. So it's a little nerve wracking. Anyway, funny story. Always feel like a fool in front of your boss, right? And it's not kind of the normal.
Never give up your leverage.
Okay. What are we at? 318. So I told you that what the plan was is we'll kind of go over plane strain, plane stress, and plane strain. And I'm going to do a very simplified view, just kind of, sketch out kind of what it looks like and kind of what the general equations would look like. I'm not going to get into the pages and pages and pages of theory behind it. You guys ever got to take an elasticity course, then you would definitely do that. But we're going to get kind of down to the punchline to see what it looks like. And then I found this problem. It's actually a dynamics problem that I wanted to share with you because it's a good introduction to finite elements. Because it's actually a string problem. It's a one-dimensional string problem where you have to discretize it and calculate displacements, where it's the theory anyway behind it. So we'll basically derive the displacement equations for this string problem, not using finite element methods, but we use, I think it uses Lagrangian or extended Hamilton's method. I don't remember. I just briefly found it. So kind of show you that to kind of get your mind spinning a little bit about different problems and kind of slicing them up and breaking them up into different components. So we'll take it kind of light today. So the topic is plane stress, plane strain. And has anybody heard those terms before? I see.
Of course. Why not?
Seriously?
Like plane stress, isn't that like one of the main things we deal with in all of our undergrad just because it's simplified?
Kind of, but when do you use it? Plane stress.
I've been doing homework all day. I don't know.
Okay.
Not in the homework I was doing.
So plane stress is a condition that you assume when you have like thin plates, right? Very, very thin plates. So we have thin plates, and I guess we need a coordinate system here. And we'll just do X, Z, and Y. And we have a condition where we can have, let's see, sigma X, Y, opposite sigma X, Y. Actually, we could write this like this. Hold on. So it corresponds to both. And then out of the edges, we have sigma YY. Sigma YY. Sigma XX. So I guess some of the bullet points where plane stress corresponds to a condition where all three out of plane components of stress are identically zero. Throughout the region. So what that means, sigma ZZ, sigma ZX, and sigma ZY are all identically zero. So we have no stress through the cross section of the material. It's super thin, and I always think of this as like almost like a plane, you know, just infinitely thin sheet. But I think the big but is the Z component strains are not necessarily zero. For plane stress in the XY plane. The magnitude of these strains Z component and depend on the constitutive equation. EIJ J is equal to R I J K L sigma K L, which is also equal to compliance I J K L sigma K L. So the magnitude of our Z component depends on that constitutive equation. The out of plane normal strain ZZ is non-zero for materials having a non-zero Poisson's ratio. For the case of plane stress and the XY plane, our equilibrium equations reduce to this: partial sigma x regards to x plus xy y equal to 0. y. And our compatibility equation becomes two times our strain xy with respect to yx equal to epsilon x y epsilon y x. So if you remember from like ME180, you can calculate stress in the z direction, right? Because we're going to have a strain because of Poisson's ratio, and if you decide that you're going to use Hooke's law to do that, then you could calculate a stress, but you would be wrong, right? It's kind of on the user to understand that that stress is identically 0 through that cross section. Now, what does it mean to be identically 0? Or what can be implied with that? And it's not written explicitly in the definition, and it's a little annoying, I think. But
Does it mean that each component is 0?
they're trying to say from this definition of plane stress and plane strain that our out of plane stress, so our zxx, our sigma zz, our zx and zy, they're all 0. But in reality, what this really means is our out of plane stress, our coming out of going through the cross section, is constant. We have a constant stress throughout the plate. And I think that's an easier way to rationalize this, is if you had a super, super thick plate and you were to pull on it, you could visualize that stress through that plate may vary if it's super thick, because you could have discontinuities and things in it. But if it's really thin, it's so thin that it's going to be a constant value in it. So I think it's a better way of thinking about it than thinking that it's 0. Because I always had a hard time with this. It's like, well, you're basically telling me for this thin sheet that Hooke's law is not valid in the z direction. There's something going on with the material, but really think a better way to think about it is that the material is so thin that it is possible to have some very small relative displacements that will give you strain. But it's so thin that there isn't a very large gradient. So the stress through it is going to be constant.
So they're basically saying for theoretical calculations, you treat it as 0, but in reality,
Yes,
a very small and negligible.
exactly. Exactly. And I think a better way of thinking about it is that it's a constant stress through the cross section. I mean, think about if you had like a piece of paper, for instance, and you were pulling on it like this, you're out of plane stress. There's going to be something, right? You're going to be able to calculate something, but good luck measuring it. You're not going to be able to measure it in practice. But there will be something there, and it's so thin, there's not enough distance, if you will, to have any kind of stress gradient. Let's say that this is your cross section here, and maybe this is also like a scale of I don't know, say 0 to 100, and you have very low stress on this side, and as you go through it, kind of your stress profile kind of goes like that to a higher value, so you have a higher stress on one side than you do on the other side of the sheet. You can imagine if you had like a theoretical plane or a sheet of paper or something, it would be very hard to have this non-continuous stress throughout, because you'd essentially be talking about, you would have like this little slice that you're talking about, super, super thin. And in that case, it's pretty close to constant through the cross section. So it's just not enough volume to get a gradient. And this, you won't find that, kind of in any textbooks or anything. But if you're doing calculations on things, there's just not enough volume of material there to give you any kind of meaningful displacement, to give you a meaningful strain, and using Hooke's law to give you a meaningful stress. So it's pretty darn close to 0. You'll get like residual values. So it's just commonplace to say, yeah, we just treat it as 0. If you're dealing with really small sheets, ignore the out of plane stress. But there could be something there, and more than likely it's constant. So, and then the opposite of this is plane strain, right? And that's where you have a nice big big cuboid. So plane strain. And this is a very good picture. Maybe we just write out the bullets first. Let's do the bullets. Well, the photo I have here is kind of just a yeah, I don't like that. Exaggerate it. And our coordinate system for this guy is X, Z is the long axis, and Y. So our X and Y are relatively similar, but our Z axis in this case is really, really long relative to our X and Y. So it's a little bit different. It's the opposite of our plane stress where our X and Y were pretty close, but we had a really thin plate. This one is really thick. So what are some of the key aspects? Corresponds to all three out of plane components of strain. So all three out of plane strain components. So epsilon z z. Y are 0, while stresses are not. So it's the opposite. Something to note is these stresses are at most functions of X and Y. And sigma z z is generally non-zero. So equilibrium looks like partial sigma xx regards to x. It's the partial sigma y regards to y to 0. Partial sigma x y x y y 0. Where sigma z z is equal to a function of x and y. Stresses are considered independent of z. So compatibility looks like this. and it's the same. So once again, it's kind of up to the user to say, oh, I have a really thick, long component. You know, I'm looking at this. This cross section in here. And, you know, my Z is really long relative to my X and Y. So I'm gonna assume that my strain out of plane in these are 0. You can calculate it, but it's going to be kind of in the noise. So when it comes to finite element methods, it doesn't come into play at all. It's just you calculate displacements regardless of this, and then you use your constitutive equation to find your stress. So finite element method won't take that into account. It's up to the user to say, oh, this is a thin plate, therefore I'm not gonna, you know, pay attention to the stresses going through the cross section, or oh, this is a really thick modulus here, I'm not gonna pay attention to the strains going through this. I'm only gonna focus on stresses, or vice versa. But
Right. Yeah, if you were using like shells or surfaces, you wouldn't really. You're kind of assuming there's no. It's plain.
yeah,
Plain straight.
Yep.
Yeah.
Yep.
So you're not worried about the thickness, the stress through the thickness.
Mm-hmm. That's right. Okay. So that's a little bit on plane strain, plane stress. There is one other topic it would have been cool to really get into, but we need like the whole rest of the class to do that. There's some stuff that has to do with bending and what really goes on in a simply supported beam. But in general, it's kind of an interesting topic, and I'm just going to talk to you about it very conceptually, just to kind of so you know that there's something going on there. So in undergrad, like when we did statics and ME180 and all that stuff, when we had a simply supported beam and we applied a load to it, and remember when we used to, you know, try to calculate this displacement? You guys remember doing that?
Yeah.
And, you know, we did it by hand, doing integrals and stuff like that. And then, you know, they told us about Rourke's and the beam tables and things like that made it a lot easier. Do you know what assumptions went into this? Well, let me try to remind you of some of the assumptions. One of the big assumptions that was going on with this is we assumed that when this beam deforms, that it's basically deforming in a very uniform planar section, right? That there's basically, this beam is made up of a whole series of these, like, think of it like a loaf of bread or something, these planes that stay rigid, if you will, and they're just allowing this thing to stretch, right? So if you were to look at, you know, a small section right here, it's essentially your beam, maybe this side stays here, but this one kind of goes like that, right? So you get stretch here and compression here. So this guy gets longer. This guy gets shorter. And we had this thing that we called the neutral axis, right? Where this was kind of nominal. Does that kind of sound familiar? That we made that very generalized assumption, and depending on who you took, they might have pointed that out to you, but it was like, yeah, whatever, right? Tell me what I need to do to find the displacement at the end of this. But this is a very interesting point. Have any of you ever done a simple problem like this, where you calculated this by hand and then you did it by FEA and see if you get the same displacement?
A long, long time ago.
You get a different number. Does anyone know why? These planes in reality do not stay planes. They're not. So what happens when you do this, when you do that bending, you end up getting this. I'm going to butcher this, try and drive this three-dimensional, but let's try this.
Potato chip cross section.
Yes. Yes. You get potato chips. You get potato chips. And in the beam theory that you learned in undergrad, that's not taken into account. So we learned that stays in like this nice planar fashion. And, if we want to find out something that's going on that cross section, we can just figure out our distance from the boundary condition and we know what it is. But in reality, what's happening is this thing is like, it's this wonky potato chip deformation that's happening because of Poissons and stuff. And it's not necessarily symmetric on the upper and lower half of your neutral axis. So it's called Timoshenko's beam theory to study it. And it's actually very, very interesting. You end up having to do this thing where you clock around the cross section looking at the out of plane or the out of phasing of the material. So it basically warps in and out of phase, and that's what gives you that bending. And if you do that, if you use Timoshenko's beam theory, you'll actually get the same number that you do in the finite element code, or really, really within like machine precision, because the finite element code is taking that into account. So it's kind of a interesting little side note. So what I wanted to go over today is kind of, I start off the finite element section showing different ways that you can solve problems. And this one that I'm going to show you right now is very, very conceptual because it's from a dynamics perspective. And it's called the Lagrangian. Well, a Lagrangian applied to a finite element string problem. In finite element, a lot of folks, especially mechanicals, when you hear that, you immediately think this this potato sliced up into a mesh, and you have this contour and it stresses and strains and things like that. That's not what finite element is. Finite element is really just, we have a problem and we're going to break it up into discrete known areas or sections, and we want to find the displacement field of it. And it can be for a range of things. So this particular problem is for a simple beam. And let's call this little thing down here at the bottom, we're going to call it 0, but we're going to say this represents nodes. And our vertical is our y-axis, and our horizontal is our x. And let's say that I have this, I'm just making something up here, it's a string. And the length of it is just x equals L. And I'm going to break this thing up. I'm going to discretize it into evenly spaced known intervals. And I'm going to say that each one of these points here represents a node. So this is 1, 2, 3, 4, so on. And I'm going to say that this height right here is simply y x of t. So that's the displacement. So y x of t is equal to displacement. Displacement of our string. And let's say I have, these little sections in between the numbers, n, 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 we're going to call those elements. So I have n, n is equal to my elements. And I have n plus 1 nodes. And then, so this is like in my easy to understand kind of format. But I need to get this into a format a little bit more mathematically based for doing calcs on it. So I'm going to put this into a kind of a different coordinate system. And I mean, it looks the same. It's still in the XY, but I'm going to kind of call things different values. So I have my 0 and out here at the end, I'm saying that this is an, and I'm gonna make these a little bit bigger so I can write on them, but they're intended to be the same as these numbered values. So this one's 1. This is j minus 1, and this is j. So this right here, I'm calling the jth element. Let's see here. So an here is the height. So the height of this guy here is a1. This one here is actually, sorry, that's not a 1. It's ai. This one is ai minus 1. And this one is aj. And this doesn't have to mean too much at this point, but essentially what we're doing is we're creating this pseudo mapping. So we're going from this XY domain, breaking it up into elements, and we're going to go to this C domain. Is that the how you pronounce it? Yeah. How do you, what's the right way to pronounce that? XI, the Greek letter? C? That's how I've always heard it.
I've heard Z and Xi. I'm not sure.
Xi? Yeah, okay, Xi. Yeah, I think that makes more sense. But so ultimately we're gonna get to is I'm gonna kind of come down a little bit, wrong mouse. And I'm gonna blow this up to look at just a couple of elements. I'm gonna simplify this a lot. Okay. So what I need to do is I need to discretize this so things are a little bit simpler. So we have to map. We have to map from our XY coordinate system to this, this other domain. And in this domain, I'm going to say that psi is equal to 1. And here on this side, psi is equal to 0. This is my AJ height. My height here is still y x of t. And this height here is AJ minus 1. And down here, try to represent this, I have my yeah, this is kind of my connection. A is equal to J minus 1 is equal to 0. And this is X equals J minus 1 N. And this guy over here is A is equal to J equals to 2. We have to create this different space. And this problem's a little confusing for it. So J and, but it'll make more sense, I think, when we do the other finite elements. But essentially, I have this equation, which is y x of t is equal to AJ minus 1 t. And I need to introduce these variables, if you will. So theta 1 of x plus AJ t theta 2 x, where J minus 1 n is less than or equal to x, which is less than Jn. And theta j minus 1 of x and theta j of x are called interpolation functions. And there's they're not going to mean much because we're not going to get into talking about them right now, but just go with it for now. What these functions do is they provide a mathematical mapping between the XY domain and this C 1 to 0 domain. So at some point, you would have to create like a relationship of connecting those two domains. And that's what these interpolant functions do. They're kind of like, a transformation matrix. We're not dealing with a matrix with sines and cosines and things like that, but how we use a transformation matrix like the T matrix or the M matrix to go from one coordinate system to another coordinate system. That's essentially what we're doing right now, but you have to call it mathematically a different domain. It's like kind of picking your house up and moving it to a new city. You're moving it to a new domain and saying that you live in the same space, even though it's different. That way you can kind of make up rules. So the goal with FE, finite element, is to find the displacements. And to find the displacements of the string is to find the displacements of the nodes. So if you find how much the nodes move, you know the displacements. And once you know the displacements, stress and strain are easy. So finding y x of t for the jth element is simply reduced to finding the nodal displacements. So we're going to use these interpolation functions. So we're going to switch this y x of t to a y c of t. We're going to say that is equal to aj minus 1 theta 1 c plus aj theta 2 c where theta 1 is equal to theta 1, c is equal to c, and theta 2 c is equal to 1 minus c, y c of t is equal to a j minus 1 z plus a j 1 minus z. And dy dz is equal to aj minus minus j. So that's the change in y relative to c. So at c equals 0, y0 of t is equal to aj. At c equals to 1, y1 comma t is equal to aj minus 1. Okay. And then this is where the dynamic stuff kind of comes in. We're going to find the kinetic energy of the string. We're going to say t is equal to 1/2 the integral of 0 to L. Rho x y dot squared x comma t dx. I'm just gonna, we don't have a lot of time, so I'm gonna skip to the, it's kind of worked out. 1/2, it ends up being 1/2, and the sum of j is equal to 1 to n, integral of 0 to 1, rho c a j minus 1, derivative of that, plus 1 minus c j. Okay. um,
Hey, Professor, is that raised to the second power?
yeah.
And then the one just before it, that's the integral from 0 to L?
Yeah.
Okay, thanks.
There's like 4 steps in between there, but I just realized that it's 8. Problem's longer than I thought it was.
Sorry, did you say there's row density?
Yeah, it's nice. Yeah, that's what I'm missing. I went out of order here, guys. Sorry. Why it seemed just a little disjointed. I got that. So we had all that. Okay, I'm gonna do, I kind of skipped ahead with the kinetic energy. So let's come over here to the side. So I should have, after giving you a little bit more information, the relation
Professor,
yeah.
I was just saying on the previous one where it says finding y of x of t, that shouldn't be finding c of t, should it?
Where?
Just before find the kinetic energy of the string, it was finding y x of t for the jth element.
No,
That
we
just-
were. Yeah. So ultimately, that's what we're trying to find, but we're converting it to C.
Okay, got it. Thank you.
So some relations that would have been helpful before I got into the energy. So this whole section should have been plugged in before kinetic energy. So X is equal to J minus C N, or C equals J minus X over N. For the first element, X equals 1 minus C N, and dx is equal to minus N dc. So Z is equal to 0 at X equals to N, and Z is equal to 1 at X equals to 0. For the second element, so that is J equals to 2. We have X equals to 2 minus C N. C is equal to 0 at X equals to N, and C equals to 1 at X equals N. So what this is saying is we're going from node 0 to 1, and we're saying that is C01. And then we go to, so, and that's element 1. So element N equals 1, element node. When we go to N equals 2, now our node 1, we're calling C0 and C1. And we're going to go to the next one and the next one and the next one. And each one of those finite spaces, we're, instead of trying to keep track of our node numbers and saying we're going from node 0 to 1, and then the next finite thing that we're calculating, we're going from node 1 to 2, and then node 2 to 3, and then node 3 to 4. It's always C0 to 1, 0 to 1, 0 to 1, 0 to 1, but the element increments. It's a way of mapping, and it's part of the finite element method that we'll be using later on. It does the same mapping. So for energies, we have some relations. Dy dx is equal to dy dc, dc dx is equal to minus 1 over n dy dc, and dy dt is equal to first derivative of a j minus 1 c plus derivative of a j 1 minus c. Okay, so that all was just a little relations that should have went before we did kinetic energy. And then
Just scroll back to that just a moment. Thank you.
Okay. And then I'm overly going to simplify this. Then we find the potential energy. And I'm just going to go right to it. So potential energy equals V is equal to 1/2 1 over N. Sum of J is equal to 1 to N. Integral of 0 to 1. T, big capital T, which is tension in the spring, or of the string, Tx times the partial of y with respect to x. Oh, well, I mixed that, sorry. I'm gonna delete that part. Started mixing equations. T, C, aj minus 1 minus aj squared z plus 1/2 a n squared, where we have this, we assume a spring down here at the bottom, and this spring is K. T equals tension in string. So this spring represents, it could be also, it could be E, right? Or C. It's just a stiffness. Okay, we've got all that, we've got all that. Differentials. Where time? So we simplify. We simplify our energies as such. So potential becomes V is equal to 1/2 A transpose KA, where A is equal to a column vector of A1, A2 to AN. And K is a stiffness matrix. We could have very easily called this C, right? Stiffness matrix, where K is equal to this second partial of V respect to UI, sorry, AI, AJ, where I and J are equal to 1, 2, to N. Kinetic becomes T is equal to 1/2 first derivative of A transpose M A derivative where derivative of A is equal to exactly what you would think. And M equals mass matrix. So, we're not going to finish this. Maybe we can. I'll simplify it. So the Lagrangian does anybody know what the Lagrangian is? The Lagrangian L is equal to kinetic minus potential. And ultimately what you do when you do this finite element program or this finite element method using the Lagrangian is Q, we find this QJ, and this is the J generalized force. And we get a equation of motion where we have d dt partial of L. This is the Lagrangian. A dot J minus partial of L AJ is equal to QJ. And when we go through and we simplify this and we take these partial derivative, we do this and take the partials of it, we ultimately end up with this ddt partial of L regards to our A dot J minus the partial of L regards to AJ, and we said this is equal to this Q. What this equation equates to is mass times acceleration plus K, or stiffness, times A. So A is our displacement. This is an acceleration term, is equal to this Q matrix. So basically all you need to solve this you only need mass, which we know, right? Stiffness, which we know, and the force matrix, which we can solve for. So using this Lagrangian method, which is just the subtraction of energies, and there's a whole bunch of steps in between here that have to do with virtual work that we didn't get into. But we take these partial derivatives, and that gives us this form of mass times acceleration plus the spring distance time of displacement is equal to Q. And this definition I haven't given you yet. This QJ or the QJ is actually equal to the partial of this virtual work, which we're not going to get into, with regards to displacement. And this guy right here is the finite element solution for the jth element. So in this particular case, it's kind of a long way of going about it, but you go from this XY coordinate system, you discretize it, you say each one of those elements is this 0 to C space, and you come up with this notation of AJ minus 1 to AJ. This particular perspective of breaking it up looks at energy levels, and then you find the force, and from the force you can back out what the displacement is, assuming that you know the mass and you know the stiffness, which this mass and the stiffness could vary as a function of that displacement if you wanted it to, but it doesn't have to. So this is just one application of finite element method, doing it from a dynamics perspective of the Lagrangian. So it has some similarities to the stuff that we'll be doing, mainly where you have to map from one coordinate system to another coordinate system. We won't have to do energies, and we'll find the displacement fields directly rather than trying to find forces. But anyhow, long convoluted problem. Sorry, I thought it would. Thought I remembered it being shorter than this. Okay, well, I wish all of you a great break next week. Try to relax. Those of you that don't have to work, those of that you have jobs, hopefully you're not overwhelmed with work to where you can't take a breather and enjoy some time off. So have a good night, good weekend, and a good week, and we'll see you in a little over a week.